So I just want to talk about a general way of computing volumes of objects that doesn't always work, but when certain conditions are being met, it does. In my first example, it will. I'll explain it more in a minute. But it's really 2 down to 6 down. I'm going to give you a really general technique for computing volumes of certain types of solids. But let me give you a general technique first with my first example. My picture's not very good. So I meant to draw a triangle down below, just horizontally parallel to the floor. And then I brought up a 3-dimensional object. If I took cross-sectional slices perpendicular to the bottom base, they're equilateral triangles. Now personally, I don't want to draw a three-dimensional coordinate axis system. I want to wait a semester for that. That's what Math 33 is all about. And we'll yet again revisit the whole issue of computing volumes of solids in 3 space, or actually even in 4 space and 5 space, even though we can't visualize it very well. Do you think objects live in 4 and 5-dimensional spaces?
Theoretically.
Theoretically, really?
Yeah.
All right, here I'm going to get myself into some trouble. How many of you, please somebody say yes, how many of you have read Flatland? 1, 2, 3. Wow, that's probably the biggest number I've ever had. 3 of you read Flatland. Good. Why? Why'd you read it?
It's required.
Read where?
GI or something.
Was it really?
Many years ago.
Just saw it online.
Oh, cool. Very cool. Yeah, it's so old you can see it online. The first thing you see when you Google searches it, that's.
I study like computer graphics and my computer science teacher brought it up and read it after that.
Yeah, very cool. Very cool. So you guys, this is a big deal. Flatland has a story is basically this. The main character is a square. So it was in 2-dimensional space. And so this square is living in this 2-dimensional space, and there's a sphere floating around, and the sphere is really, really bored. So it wants to have fun. So up here, the sphere just looks down at the square and starts talking to the square. Well, to the square, what does the sphere look like? See, I think it looks like nothing, because the square is 2-dimensional. It can't look up or down. It's not a 3-dimensional creature. So I think what the square is thinking is that he's hearing voices. But the sphere decides it's still bored. So it decides just to touch the universe of the square, touch the plane. Now to the square, what does the sphere look like? Just a dot. And the sphere decides to pass through the universe of the square. And all the meanwhile talking, so as far as the square is concerned, he was hearing voices. Now a dot appears out of nowhere, grows into a bigger, bigger circle, and then gets smaller and smaller, poof, vanishes in thin air. All the meanwhile, the sphere is still talking to the square. So the square really thinks it's going nuts. And you and I understand the situation because you and I are 3-dimensional creatures. We can fully understand why that square has a difficult time perceiving what the sphere looks like. And for that reason, maybe you and I shouldn't be so close-minded as to thinking that maybe there are higher dimensional objects that we just can't perceive because we're lower dimensional creatures. To be honest with you, the reason why this book was written is in the 1880s, the leading mathematicians at the time, at Cambridge, England, got sick and tired of hearing all this garbage in the public talking about this higher dimensional geometry with all the science fiction at that time. And they came out and they made a declaration, in a sense saying, you public people, you're so ignorant. There is no such thing as 4-dimensional space. Stop talking about it. And the author of this text was so incensed by that, he wrote this book to shake everybody up, saying, you know, with a 2-dimensional creature, we can perceive why it has difficulty visualizing what a 3-dimensional object is. Maybe you and I have the same darn difficulties as 3-dimensional creatures. In fact, he thought he'd get in a bit of trouble for it, so he actually didn't put his name on the first edition. But later he did. The name's Abbott. I can't remember his first name.
So in a way, 4th dimension or a dimension above, outside of the dimension you're in, is invisibility?
Not necessarily. I mean, your subdimensional space might intersect another subdimensional space of a higher dimension. And so we can get these subspaces. Okay, just wait 2 semesters. I'll talk a lot more about this in Math 33. Actually, you guys don't mind. Oh no, this computer's new. Fine. Here's an example of a program that's generating a four-dimensional object over time that's passed through a three-dimensional universe. And I'm using a computer illustration with a nice program, or excuse me, a nice equation describing an object in four-dimensional space as it's passing through our three-dimensional space. Just like with the square, that circle appears as a dot, gets bigger, bigger, and bigger, smaller, smaller, and poof, vanishes. This is an illustration of that, a four-dimensional object coming through our three-dimensional space.
But it's not showing what a four-dimensional object would look like. It's just what it would look like passing through.
A particular one, yes, a particular one described by these equations, yes. All right, I'll stop. You guys, come back to my question. So remember, if I take a cross-sectional slice this way, perpendicular to the base, then I've got equilateral triangles. Let's compute its volume. Do you mind if I'm lazy and just use my math D skills? So here's the x-axis. Here's the y-axis. Can we forget about the three-dimensional object and just to the base? But with that base, can you just rotate it 90 degrees and slam it on the ink board on my Cartesian plane and do it in such a way that this vertex right here, just for convenience, is at the origin? Wouldn't that get this as my base? You guys, you know me by now. It's been one full week. Bless you. I can't draw. But can you imagine pulling up an equilateral triangle like this, and then one here, and a smaller one here, a smaller one here, down to just a point, and that would create my three-dimensional object I was trying to draw on the board over there. Can you imagine it? And so I think what you and I can do is something this silly. Let's you and I can consider a vertical rectangle. And imagine this vertical rectangle I bring up off the ink board into an equilateral triangle. Can you help me with this dimension right here? That'd be a small change in which direction? X direction. Now I think if I were to compute the volume of this ith rectangle, I said rectangle, didn't I? If I were to compute the volume of this ith triangle, don't you think its volume, oops, I don't know, I'm sticking to red. I said, don't you think the volume of this triangle is simply going to be, well, its thickness times the area of the lateral side, bringing the triangle up. That would be the area of a triangle. How would you guys compute the area of this triangle? Yes, sir?
I was just wondering about your points right there.
Yeah, I was just very curious.
Zero, did you mean, should it be 7 and 5 halves?
Don't listen to me. I don't know my numbers.
Okay, I was just wondering, okay. I didn't.
It's like, did your origins change?
I'm in a different dimensional space, okay? But you guys, do you agree with me that the volume of this triangular region in 3 space is just the thickness delta x times the area of the side over here? But how would you compute the area of this triangle? How would you do it?
1/2 base inside.
We could do that. I'm too tired.
Ooh,
What's an easier way? Well, how many ways can you compute the area of a triangle?
bunch.
Yeah, a bunch, like 1/2 base times height, and did I look in the right words? Trigonometry meaning
Sines,
which one? Which one?
cosines,
Which one?
sine.
Well, how? I feel so alone. 1/2 times the product of any 2 sides times the sine of the angle included in between those 2 sides. 1/2 AB sine theta. Hello? Trigonometry. You serious?
Yeah.
Oh, all right. Let's take a math 8 break. Is it really? It sounds to me so trigonometric. Do you guys agree, yes or no?
Yes.
Peace, K. Oh, by the way, label this side A. Consider the angle in between those 2 sides, A and B. Now, don't look at the whole triangle. Be lazy. Look at the small right triangle here. Pulling out the second piece of scratch paper. With that second triangle, wouldn't you guys agree that the sine of theta could be interpreted as a ratio of the length of side opposite to the length of the hypotenuse? Or shall I say, h could be interpreted as a times the sine of theta? Well, that being the case, let me come in here and make a substitution. I got 1/2 times the base times h, which I can now think of as a times the sine of theta. So I think the area of a triangle could also be interpreted as 1/2 times the product of the two sides times the sine of the included angle. That way I don't have to worry about this goofy h business, which is not the length of the triangle, if I so choose. This is going so well. Let's see how this turns out. Give me a third technique for computing the area of a triangle.
That's not the dot product, right?
No, it's not. I confess, there are the sine of theta could be interpreted or incorporated in the magnitude of a cross product as a geometric constant of the cross product. Oh, shoot, I forgot what class I'm in. I forgot what book I'm in. Next semester, your prof doesn't say that. He gives that as a definition of a cross product. I was really shocked. Because the magnitude of A cross B, it's not a vector. It's just a scalar. Sorry, I'll stop there. The third formula in your back pocket. You guys have back pockets, right? For computing area of a triangle? Thank you, Heron's formula. Remember the Heron's? You don't remember the Heron's formula? The square root of yeah, the square root of semi-perimeter times semi-perimeter minus one side times semi-perimeter minus the second side times semi-perimeter minus the third side.
Well, what's a
Where,
semi-perimeter?
where do you get that from, and what is a semi-perimeter?
It's Heron's formula.
I did not take that in trigonometry.
No, that's just high school geometry, isn't it?
Oh.
And the semi-perimeter is just a perimeter cut in half. Yeah, isn't this beautiful? These two formulas you can use without knowing the height of your triangle. Life's really happy there. Anyway, let's come back to my question. To compute the area of the triangle, this triangle up here, its side looked in this direction. Compute that area, why don't I just look at the product of two sides? I said, why don't I look at the product of two sides? Please? Okay, I got an idea. Label this point right here. X sub I, comma, Y sub I. Help me with this. What's this length? Y sub I. What's this length? 2y sub I. So the length of one side is 2y sub I. The length of another side is 2y sub I. Times the sine of the included angle, which is 60. Yeah, the sine is 60 degrees. But shoot, you guys, the sine of 60 degrees is a piece of cake. It really is. Truly. It is.
Root 3 over 2.
Thank you. Oh no, I'm in trouble. Look, I'm eventually going to take the limit of the volume of all of these triangles as delta x goes to 0. So eventually, guys, this delta x is going to turn into a dx. And since it's going to be a dx inside of an integral, it certainly is the case that I'm not happy with the y sub i's. I better rewrite it in terms of x sub i's. Just so you can help me overcome my loneliness. That line? This black one right here. I'm going from here to here.
7x.
Say it again.
5 half x.
Say it again.
Slope of 5 half.
What's the slope of the line?
5 half.
It's not what I got.
2
Math
fifths.
35 over 2.
I got an idea. Tell me if my words are correct. Rise over run? The rise is 5 halves, run is
7.
so rise over run is
5 halves, so
thank you,
7.
thank you. I might actually finish one example today. And by the way, the y-intercept is 0, 0. So my b is 0 with the equation y equals mx plus b. Oh, that being the case, what's another name for y sub I then? 5/14 times
X
x
sub I.
I. Doesn't that give me 5/7 twice times y sub I squared? I misspoke, didn't I? I meant to say x sub I squared. But if that's the volume of the ith rectangle, then I think adding up all those the rectangle's volumes, taking the limit, as delta x goes to 0 means the volume of the object I tried and I did a lousy job in the picture on the left-hand board can be computed by looking at the integral of my, is that x squared with respect to x? Can I give myself more room for the coefficient? Pulling that coefficient out in front, does that give me a 25 root 3 over, I don't know, is that a 98? And I'm integrating from 0 to 5 now. Man, you guys do a good job being quiet.
Stupid question. Where did
Yes.
the sine of 60 come from? Or not the sine of 60, but 60 degrees in
It's
general.
equilateral triangle.
Yeah, I said it in
Oh,
words. I
oh,
was talking about equilateral triangles coming up together. Oh, come on, you guys.
Actually
You're
integrating to 7,
to what? Where'd you get that?
0 to 7, because you're going this direction.
I agree. Think about it. This integral represents the limit of a Riemann sum. What the heck am I summing together? I'm summing together the volumes of these rectangular solids in 3 space. And I think relative to my 2-dimensional cross-sectional slices, my 2-dimensional rectangles, they're ranging from one leftmost extreme of 0 to a rightmost extreme of 7. I think I got to change everything. Well, actually, maybe not that one. But certainly, I'm looking at an extreme for the x variable from 0 to 7. Everybody there? Does that give me in the end 25 root 3 over, I don't know, you guys help me with this. Is that 294 times x cubed from here to here? You guys are making me do all the work.
Yeah, I got you. Alright, looks like you got it.
Can I stop? You don't trust me. Yeah, there's not much else I can do with that. Questions? So you guys, all I'm suggesting is there is a technique for computing some volumes, given enough information, where I can just look at cross-sectional slices. That's not what I want to discuss today. I want to discuss something so much more interesting. You guys, can I leave this first example? Okay. So I can erase.
Wait, when you take the integral of the volume, you don't get surface area, you get area. Because the volume equals that, right?
Yeah, the reason why I'm saying volume equals is think about it for a minute. Remember this came from delta x. So it's got a certain unit associated. Can I just make one up? Inches. But x is measured in inches as well. And so I think I've got inches twice and one more time makes cubic inches. And as far as I'm concerned as a mathematician, just simply means I'm adding things together. So I'm adding a bunch of things whose units are in cubic inches, and the result's going to be in cubic inches. Give me the volume that you measured for each. In case you think I made a mistake with my units.
No, but I meant like if you were to take the integral of the volume equation, you get area or surface area. Like when you take the integral.
Neither. Shoot, I shouldn't say it that way.
It's like when you take the integral of velocity, you get is it speed or distance?
When you take the integral of velocity,
Yeah,
you're going to get position. I'm just not interpreting it that way. In this particular example, I'm interpreting this integral as really just giving me the sum of these individual volumes. You're thinking like the author of your text. He says, think of that this way. Got some constant out front. Integrate from here to here. And let's integrate the area. And that'll generate a volume value. That's what he writes. I just maintain, silly. I got area, which is 2-dimensional, times another dimension, which collectively speaking gives me a 3-dimensional object. So if you want to suppress the flag to which you pledge allegiance, you're right. We're jumping up 1 dimension in space. Me as a mathematician, I think of that already in that space because I assign units to that particular expression before I take the limit that delta x is delta x goes to 0.
I'm not even sure where x squared came from, but no,
Yeah, piece of cake. First things first. Do you see where these two factors came from?
No.
Was that? Did you say no?
No.
Good. Okay, I'll go back then. So that's not gonna make sense unless I go back here. What I was really doing is this. I was saying, nifty little horizontal rectangle there. And if I break it in free space, does it look something like this?
Right.
And now, if I can think of this length right here, I forgot what it was. It was, I can't hear you. Really? See, I had a bigger picture like this.
It was 2 ones.
Yeah, I think this was y sub I, because I was talking about an arbitrary point here. So, sir, if I think of that point as x sub I comma y sub I, and remember how my x-axis ran here, my y-axis was here, then I think, with my brace, this length right here is just a y-coordinate point. That being the case, watch my green pin. I think this length right here is going to be twice that because of all the symmetry in my picture. And if this length is 2y sub I, oh, don't forget, I may not have written it, but I said these cross-sectional slices, these triangles, are equilateral, which means this length right here is 2y sub I. This length right here is 2y sub I as well. So I was computing the area of the triangular face as 1/2 times the product of these two sides times the angle in between, but since it's an equilateral triangle, that was merely a sine of theta. That would be the area of the I face. Do you see it? Wow, you guys, you know what? I don't see it. I really think I made a mathematical error here. What did I forget? I really did. My apologies. Sir, I know I have not answered your question with the x of i's, but just because, you know, answering a question, I noticed I made a mistake. Can I just fix it real quick? It's an easy fix. I'll cheat.
Ta-da!
And finally, to answer that original question we had, check this out. I think when it comes to this boundary, that line right there, since this point really was located here, I think I could describe this line as an equation. In fact, if you don't mind, can I be this lazy? Can I think of this as a y equals mx plus b? As the equation of this line right here. But I got lucky. I got lucky because the way I created my Cartesian coordinate system, this line passed through the origin. So I know b is equal to 0. But I also can observe exactly what the slope is, because running from this point to the other, the amount of rise, the amount of run, is 5/2/7. That's where I got that slope value, 5/14. That being the case, notice that since the thickness of this triangular region in free space is a small change in the x direction, that's where the delta x came from. Since when I'm going to eventually take the limit as delta x equals 0, that's going to turn to a dx. That means in the integrand's position, everything's going to have to be expressed in terms of variable x. I'm in trouble. I'm in trouble because if you can see where the two y's come from, notice that they're in terms of y, not x. So I took a break and I said, this equation, x is equal to 14y over 5. I misspoke, didn't I? I didn't misspeak. I'm just saying I don't need that. All I was suggesting is that another name for this y sub I is 5/14 times x sub I. Did you see it? And I know I didn't write a 14 because I canceled a 2. But it really came from the equation outlined in green. Is happy? Okay. Then I'm going to erase. And before I answer my second question, I want to draw a pretty picture. Here's my pretty picture. It's one I'm sure you've never seen before. And if you guys allow me, and cheapers, I sound like a broken record. In my traditional fashion, I'm going to subdivide the region from A to B into n subintervals, And if you guys don't mind, just to be simplistic, I'll make it a regular subdivision. And what I'm going to do in the end is this. I'm going to look at the bounded region under my curve, from A to B. I'm going to take this region and rotate it off the inkboard into three-dimensional space, 360 degrees all the way around. And I think if I do that, what I'll end up generating is a three-dimensional object that kind of looks like this.
Pretty vase.
A pretty vase, yes. Or an odd-looking speaker. As a matter of fact, if ever I play this game of taking a two-dimensional region and revolving about some line to create a three-dimensional object, I might refer to that three-dimensional object as a solid of revolution. And what I'm going to do now is develop a whole new technique for computing the volume of such a solid of revolution. This technique, I might as well give a name to it. It's called the disk method. So can I erase my three-dimensional object? Go back into lower two-dimensional space. And if you allow me to do that, then like I said earlier, if I subdivide the interval from A to B into n subintervals of equal length, I think here's where they are. Here's an arbitrary I subinterval, and here's my last subinterval. Now I maintain that over the I subinterval, if you guys allow me to choose an arbitrary value of x, let me call it x of I with a bar over it. I'll use that x value to go straight up to my curve. Use that to determine the vertical height of an approximating rectangle. And I will revolve that horizontal rectangle about the x-axis, one full revolution, to generate what ends up being nothing more than a disk. Did you guys see it? How do you compute the volume of that disk? You took way too long.
Pi r squared.
Pi r squared times delta x.
Yeah, the volume of is going to be the area of the base times its thickness, its height, which in this case is a small change in the x direction. Oh, but shoot, another name for the radius is
F of x.
yeah. If you consider an arbitrary point right here, x sub I, y sub I, or actually x sub I bar, y sub I bar to be consistent, then I think I've got nothing more than y sub I bar. Or like Randall, you said, I could also, if you want to, think of this as f of x sub I bar squared. Oh, but shoot, you guys, that's only the volume of the disk over the I subinterval. I made a mistake. I wanted all of them. If I read 10, I'll choose another value of x in here. I'll call it x sub 2 bar. I'll call this x sub 1 bar. I'll call this x sub n bar. And I will look at those approximating rectangles, rotate them about the horizontal x-axis, get a bunch of disks, actually n of them. And if I sum them all together, I got an approximation for the volume of the solid of revolution. Ah, but if I take the limit of that sum, as delta x goes to 0 or as n goes to infinity, I generate a definite integral. And here's what it looks like. Taking this beast, putting it in the Lagrange position, the volume of a solid of revolution, after taking limits, is going to be pi times the integral from a to b of my function's output with respect to x. And I'm integrating with respect to x. That would be the nifty form in my back pocket to generate the volume of a solid of revolution using this whole new technique I'm going to refer to as a disk method. So everybody, here's my first question. What's the formula to generate the volume of a sphere? 4 thirds pi or shoot, why?
I think we're about to find out.
Because your high school geometry teacher told you so. Ah, but now it's proven.
Yeah.
Can I erase this?
Yeah.
Ah, that's not a real eraser. So I know you guys, if you go to a party and somebody says, let's have some fun, let's compute the volume of a sphere, you know, most people say, just get a further part. But next time you go to a party, what you could do is this. You could say, oh, don't look at the sphere yet. Let's look at a semicircle whose radius is r. And now if I draw in a nifty little vertical rectangle, then maybe I can rotate this rectangle about the x-axis to generate that three-dimensional solid of revolution that we typically refer to as sphere. But the volume of that little disk can be computed the same way. It's nothing more than pi times the radius squared, and I'm going to integrate with respect to x. And I think in terms of a definite integral, that looks like the integral of my pi times my y sub I. Oh shoot, I guess I don't have it because I need everything in terms of x. Anybody? What's the equation of a circle?
R squared.
What's the equation of a circle?
Oh,
X squared plus
Y squared.
equals R squared. Well, I take that back. That's the equation of a circle if its center is located at the origin. But doesn't that necessarily imply that y is equal to the square root of my r squared minus my x squared? Ah, but I'm squaring it. Do you guys mind if I cheat with my bounds of integration? I know this should be negative r to r, but can I exploit the symmetry here? Let's just integrate from 0 to r and double the result. But that simply gives me 2 times pi times the integral of r squared minus x squared with respect to x. But that gives me 2 times pi times, is that r cubed over 3? I asked, is that r cubed over 3?
Yes.
No. Integrates by x. R is just a constant.
Oh, yeah. That's just x.
How about r squared times x?
Oh, yeah.
Okay, as long as you're happy. Minus,
X cubed over 3.
and I'm evaluating from here to here. Or shall I say, I've got 2 pi times, is that an r cubed minus 1/3 r cubed? Or is that 2 pi times 2/3 r cubed? Which is, oh, look at that. 4/3 pi r cubed. This is why my wife doesn't take me to parties anymore. There. If you are, let's start flying with this. Look at my next example. If I were to graph y equals x to the 3 halves. I don't know, you guys, can I stop talking for a minute? How do you graph this really quick in your head? I'm just being honest.
It's cube root, so it's basically.
It's
actually
not a
cube
cube root,
squared.
it's square root cubed.
I don't know what that looks like.
It goes faster than 1. Now that's true, but it's also growing faster than x to the I like the way you said that the first. Think about it. Y equals x to the first is just simply this diagonal line. But since the exponent is bigger than 1, don't we have curvature that goes in the upward direction instead of downward direction? If that were 2/3, I'd have concavity in the downward direction because that exponent is less than 1. That's what it's getting at. So I think more accurately, graph looks something like this. Well, at least in the right-hand plane. Oh, I guess I never really wrote the full question. Do you think I can take some limitations here? Let's allow x to be ranging from 0 to, I'm just making this up, you guys. How about that? 4. Then in my picture, I think the portion of the curve I'm looking at is going to be this. Where this point right here is going to be 4, 8. And here's the region below the curve as x ranges from 0 to 4. I want you to take that region and revolve it about the x-axis. And if I revolve this region about the x-axis, let me draw a nifty little red vertical rectangle. And let's see what happens when you and I rotate that vertical red rectangle about the x-axis. I get something that kind of looks like this, a little disc. Or how about if I say this, more globally speaking? Rotate the entire black region around the x-axis. I get something that kind of looks like a speaker cone. Let's do it. I concentrate just in the red disc. I think the volume could yet again be computed by looking at pi times the integral from a to b of the output of my function f in terms of x squared and integrate respect to x. But jeepers, in this example, that just gives me pi times the integral from I don't know where to I don't know where. And if I'm integrating with respect to x, then I think my bounds of integration should be the extreme values for x. In other words, how do I stack up these rectangles? What extreme left and right positions do I have on the x-axis for those vertical rectangles? 0 to 4. Well, my function f's output is explicitly given as x to the 3 has power. That's what I'm going to square. I guess that gives me pi times the integral from 0 to 4 of my x cubed with respect to x. Or shall I say, that gives me pi over 4 times my 4 to the 4th. Is that a 64 pi? Oh, did I forget my units? I'll put it in. Is that okay? Is that okay? Yeah, maybe, because I'm using a silly word units. But if the units are describing values in the x-axis, wouldn't this generate cubed units? In other words, I'm just trying to shake you up. Remember, it's a volume that we're computing. You guys, so far so good?
Yep.
All right. Oh, you know what, you guys? I don't like my question. Shoot. Let's do this. Consider the same region. Let's compute the volume of the solid of revolution generated by revolving this two-dimensional region. How about something else? And if here's a line y equals -2, what do you think that region is going to look like? I misspoke, sorry. What do you think that solid is going to look like?
It's a nice same thing with a big hole in the middle.
Yeah, it sort of looks like a wash or a nut with a big hole in the middle.
Hole of radius.
Can you guys picture that?
Yeah.
Just to save you from the pain of watching me draw.
It's the washing.
Washer method.
Shoot, you guys, you're right. I can't do this. I guess a disk method doesn't apply anymore, so I got to take another break. Man, we're so big I have no sideboards to use, huh? Can I erase this?
Yeah.
X-axis, y-axis. Y equals f of x. Y equals g of x. If I were to look at the region in between these two curves as x ranges from a to b, and revolve that region about the x-axis, then I think one of the rectangles I'll be taking into consideration is this one right here. Let me take a peek at a couple points. If this point right here on this border of the rectangle is going to have an x-coordinate and x of y, isn't this y-coordinate just f divided x of y? And I think if I were to take a point down here whose x-coordinate is